So imagine trying to unclog a pipe, but this pipe is like 7,000 meters straight down into the earth, and it's baking at 150 degrees Celsius.
Yeah, that is definitely not your standard plumbing problem.
Right. And normally, clearing a massive blockage down there means, bringing in heavy explosives or pumping down toxic chemicals or dragging out a massive, expensive drilling rig.
It's a huge logistical nightmare, usually.
Exactly. But what if you could clear it out using essentially underwater lightning?
It sounds totally crazy, but it's happening.
It really does. So welcome to today's deep dive for you listeners out there. Our mission today is unpacking a technical presentation from a company called Oildynamics. We are looking at their DSWS 38mm EHV.
And just for context, EHV stands for extra high voltage, which gives you a pretty great hint about where this technology is going.
Oh, absolutely.
Yep.
So to start, I'm really trying to wrap my head around the power source here.
Yeah.
Because they obviously can't fit a power plant inside a tool that's only 38 millimeters wide.
Right, which is just about 1.5 inches.
Yeah, it's tiny.
Yeah.
So are they sending the power down a wire from the surface or like storing it up inside the tool somehow?
It's actually a bit of both. They send electricity down what's called a standard logging cable,
Okay.
which is basically the industry's heavy-duty extension cord for lowering sensors into a well, and that trickles power down to charge a series of high-voltage capacitors inside the tool itself.
Oh, I see. So it builds up the charge.
Exactly. And once it's fully charged and in position, it just unleashes this massive streamer discharge.
So it's discharging it all at once, like a controlled miniature lightning bolt right into the fluid inside the well.
You nailed it, and the power is staggering. It hits a peak of 300 megawatts in a fraction of a second.
Wait, 300 megawatts?
Yeah, that instantaneous discharge flash boils and evaporates the surrounding liquid almost instantly.
Wait, let's unpack this. So the liquid rapidly expanding creates a massive sonic boom straight into the rock.
Right. It generates a mechanical shock wave, an impulse of 50 megapascals, and that travels outward at over 2,000 meters per second.
Let's put that in perspective for you. If you were somehow standing next to this underwater, that 50 megapascal wave is roughly equivalent to being hit by like 500 times the pressure of the Earth's atmosphere.
It is an absolute sledgehammer.
But wait, if this thing is hitting like a sledgehammer, how does it know what to break? I mean, why doesn't it just shatter the metal well pipe and the cement holding the whole well together?
That's where the physics get really, well, elegant. It comes down to acoustic impedance.
Meaning different materials react differently to the shock.
Exactly. Brittle materials, like hardened scale, salts, and thick drilling mud, they absorb that shockwave very differently than the steel pipe does.
Okay.
The metal casing is actually flexible enough to absorb and pass the wave along completely unharmed, while the brittle blockage just shatters.
Oh, wow. So the pipe just flexes.
Right. And the impact also excites compression and tensile waves that expand tiny fracture networks in the rock itself. They call them worm channels.
Worm channels, I like that.
Yeah, and expanding those opens up the flow of oil without ruining the expensive infrastructure.
Wait, I have to stop you there, though.
Yeah.
I buy that the steel pipe survives because it's flexible. But if this tiny 1.5-inch wide tool is constantly unleashing 300 megawatt blasts.
At extreme depths, yeah.
Right. And baking in 150 degrees of geothermal heat, how does the tool itself not just melt or blow itself to pieces?
You'd think the heat would destroy it instantly, right? But the secret is in the timing. That massive pulse happens in fractions of a microsecond.
So it's too fast to melt it.
Exactly. It's so incredibly fast that the extreme heat simply doesn't have time to transfer into the metal casing of the tool. The surrounding fluid absorbs the energy, creates the shock wave, and dissipates before the internal components even register a temperature spike.
Okay, that makes a lot of sense. So because we are using this ultra-fast precision shockwave, instead of, a massive physical drill bit or a toxic chemical soak, that completely changes the physical footprint of the operation on the surface, doesn't it?
Oh, it changes everything. You don't need a heavy drilling rig at all. It's totally rigless.
Because the tool is so slim.
Right. They just lower it directly through the existing production tubing on a wire. And to make sure they hit the exact spot 7 kilometers down, they use integrated gamma ray and casing collar locator sensors.
Which I'm guessing aren't just fancy cameras.
No. Cameras wouldn't work at all in that dark, muddy environment. The gamma ray sensors actually read the natural background radiation of the different rock layers.
Oh, that's wild.
Yeah, it creates a subterranean map, letting the operators know their exact depth with pinpoint accuracy.
And doing it this way means you avoid what the industry calls well killing, right?
Yeah.
Where you have to pump heavy damaging fluids down into the hole just to control the pressure before you can safely work on it.
Exactly. This is a clean, purely physics-based approach, which means operational costs absolutely plummet.
Because there's no heavy machinery.
No explosives to transport, no hazardous materials to clean up, and the well can return to production almost immediately after the pulsing is done.
It really distills down to this for you listening. Oil Dynamics is utilizing extreme but perfectly controlled physics to optimize deep well production safely and cleanly. They've basically taken what used to be an expensive, toxic, heavy machinery nightmare and turned it into a fast, precise lightning strike.
It really highlights how far applied physics has come when you harness it correctly.
It really does. And it leaves me with this final thought for you to ponder today. If we can perfectly harness these ultra-precise, miniaturized shock waves to clear blockages 7 kilometers deep inside the Earth, well, what other deep-seated blockages could this type of miniature lightning eventually solve?
That's a great question.
Right. Could we use it to open up clean geothermal energy? Or even miniaturize it further for internal medical applications inside our own bodies? Definitely something to think about.